So what exactly is resonance? That's the first thing. Do you need to copy this down? No. If you already know what resonance is, then you don't need to copy this down word for word. Resonance is a natural tendency for an object to want to vibrate. All right. So any physical object out there has this natural frequency to want to resonate, okay, or to vibrate. For example, this ruler over here, if I flick it, you'll see it just naturally wants to just go back and forth. Okay, and that is its natural frequency. Okay, and that's all resonance is. In fact, what I do as a demonstration over here is that in a classroom, I would have these two tuning forks connected to a big box. And the whole purpose of the big box is that the box is called a resonator box. It's one that's been mathematically calculated out that it will allow the sound to become amplified. Okay, and I have two exact clones of these boxes. Okay, box on the left and box on the right. Now, when I strike the tuning fork on the left, all right, so I use a little mallet. Here's my terrible picture of a mallet, and I strike it. The tuning fork will vibrate. It'll be amplified by the box. The box will send the sound to the second box. And since the second tuning fork is at the same resonant frequency as the first box, here's the trippy part. I block this with my hand, so I use my hand and I hold onto the tuning forks, and I silence it, and the whole class can hear the second box start to vibrate. Okay, so every object has its own natural frequency, and if you hit that natural frequency, you'll cause it to want to shake. And to prove that this is true, the next thing I do is I take the first box and then I add a little bit of weight to it. And by adding the weight, I increase the inertia of the times. With the increased inertia, it vibrates just slightly slower. It loses 2 or 3 hertz by adding that extra weight. So I strike it, I make a loud sound, but this time around when I cover it up, the whole class hears nothing but silence. Since these two are not matched up in frequency, the second box doesn't resonate with the first box anymore. And that's what resonance is. It's a natural frequency of all objects. And that's what we're going to get through today. Okay, we're going to find out the natural frequency of certain objects and then exploit that. Okay, I do have a video to share with you. I can't go through the whole thing because we're pressed for time, but I'll cut to the chase. You probably heard of stories where if a person sings and they're singing at the right pitch, you can cause glass to shatter. And this is somebody on the internet who was able to successfully do that. Okay, it is a rather long video and I just don't have time to go through all of it. So I'll just cut to the chase where she finally hits to the right target, which is somewhere over here in the video, and we'll go from there.
Can I try a bit more time? Okay.
There you go. A bunch of nerds having fun. In fact, the show is called Festival of the Spoken Nerd. All right. So yeah, if you have a chance to check out this UK group, they're pretty funny in a nerdy way. Okay, so just as a reminder with regards to transmission of waves, this is the natural behavior of waves when they hit a junction point. Okay, so when they end up hitting a brick wall, right, so a fixed rigid object like a doorknob, you'll end up having a reflection that will reflect back upside down. So you'll always have an inversion in a fixed end reflection. That happens every single time, okay, as you can see in the animation. It always flips upside down and returns back. On the other hand, with an open end reflection or a free end reflection, this is one where, if you recall, you drew a circle. Right? This is one where you allow the wave just to freely whip. In other words, you're going from a medium to essentially a vacuum. So you're going from something that's dense to something that has no density whatsoever. It always ends up bouncing back upright still. Right? So if it was a crest coming in, it will reflect back as a crest. If it's a trough going there, it'll return back as a trough. Moreover, here's the other interesting point. Okay, you can take a look at the initial amplitude of the wave. Suddenly, the amplitude of the wave has now doubled. All right, so in other words, it suddenly got louder. And again, the reason why it gets louder is because now you're adding the incident wave that's positive with another positive wave. And when you add positive, positive, you end up getting double positive. And that's why temporarily it gets suddenly louder. All right, and with regards to resonance columns, they all rely upon that principle. If you could figure out how to line up everything just perfectly so that you have an anti-note at the edge, you can amplify the sound. Okay, so now let's just talk about this stuff with regards to sound now, because right now we're only talking about it with regards to mechanical waves, right? This is a physical string, either tied up to a doorknob or it's connected to just a rod, okay? And it's able to freely move up and down on the rod. Again, you can try doing this demonstration out yourself as well. You have a very thick rope, tie a little circle to it, hook it to a broomstick, and when you whip it side to side with someone else in the family member helping you out, you will get this outcome. And if your family member decides to hold on to that rope on the far end, you'll see that when it hits your friend, it will reflect the other way around and come back inverted. That happens every single time. And the same thing also happens with sound as well, when sound goes through a chamber. And there are two types of chambers. There's a closed-end chamber, and then there's an open-end chamber or open-end resonance. Okay, so let's just talk about what happens in each case. So the dotted line that you see over here, this is just telling you that, I have a very, very long tube, kind of like the tube right over here. Okay, so I have a long tube lying around. As I said, guys, I hope you guys have been saving up on this because your end of year project will require you having tubes. If you don't have tubes around, you can easily use pieces of paper and roll it up. The only catch about using pieces of paper is that when you roll it up, all 5 of your tubes have to be identical in diameter. And that's going to be challenging to do. Okay. And that's why I said, if you can find stuff that's prefabricated, that will save you that effort of ensuring that they're all the same diameter. Okay. All right. So here's the thing. As sound travels through this tube over here, it'll create compressions and rarefactions, compressions and rarefactions. And the moment it reaches a junction or difference in medium, one way of doing it is to go from the tube to space. And the other one is to go from space to your hand. It will change the outcome of how it resonates. All right. Someone was asking about toilet paper. You could use toilet paper rolls, but what you want to do is that this is too short. You want to tape a second roll on top, and it will work out. Anyways, let's stick with this stuff over here. We'll talk about the lab afterwards. Again, this is all being recorded, so I want to just stick to the topic. All right. So this is a case where a wave travels through the tube, and then it ends up hitting something solid, like your hand, for example, or a piece of paper on the other end. This will cause the sound to hit it and bounce off of it negatively. So here's the animation. Beautiful, isn't it? A bunch of dots that you're trying to figure out how to draw. And here, this is the problem about trying to describe longitudinal waves as a bunch of air particles. When you draw it this way as a longitudinal wave, it's just a mess of dots. And I tried to color code them so you can see which ones are crests and which ones are troughs. And you can see it's just a big fat mess, all right? So instead of drawing it this way, which I don't expect anyone to draw in their notes this way, let's just draw it and represent it as a transverse wave. That way you can clearly see what's going on. Again, you're transmitting an incident wave into the tube, it hits a dead stop, and it's going to cause the wave to reflect and return back inverted, right? So the wave that's traveling in, the moment it hits that dead stop wall, it's like a doorknob, it's going to hit it and reflect and return back inverted. And the opposite happens when you allow air to travel from a medium to a vacuum. Now, the truth is that outside of the tube, it's not a vacuum, but there's a lot of air to freely move around. You're not constricted like you are inside, all right? So unfortunately, the air that's inside, it suffers from, what's that word? The fear of being in closed spaces. Some sort of phobia, I forgot the word, okay? So they're suffering from the phobia inside here, but they're freely able to move outside. I think someone's gonna tell me the word, or someone typed it out.
Claustrophobia or something?
Thank you, claustrophobic. Oh my gosh, I forgot that word. Thank you. All right, yeah, so they are a little bit claustrophobic inside the tube, but outside they're freely able to move. So you're going from a medium to effectively open space. All right, and this is what happens to the sound when you have the air go through that. Okay. Here's a picture, and as I said, the picture of dots is hard to follow with the eyes, but as we described before, when you go from a medium to open space, you end up having an open-end reflection. Okay, so you end up creating something that looks like this. Here's a transmitted wave, and here's a reflected wave. I'll animate it for you one more time. Okay, here's the incident wave, and you can see that you form an open-end reflection over here. And it returns back the same way. Okay, so this is case A. Case B, well, what if you transmitted it, but it was like this, where instead of being a crest, it was a trough? Well, if it reaches the boundary as a trough, like in this animation over here, then it's going to reflect back and return back as a trough. And I have those animations down below so that you can correlate, what I'm talking about with the animations from the previous slide. Okay, whenever you have a fixed end reflection, like right over here, you'll see that the wave returns back inverted. Meanwhile, in an open end reflection or a free end reflection, if it comes in as a crest, it will reflect back as a crest. If it comes in as a trough, it reflects back as a trough. Again, nodes and lobes are different, all right? I'll just use this diagram up here just to describe those words. Yes, there will be nodes formed over here, all right? So that's known as a node. And over here, it's known as an antinode or antinode. And sometimes when you're looking at it verbally, they'll just say, count the number of lobes. So that's why an antinode is often like visually called a lobe, like an earlobe. All right, so those words, they can more or less be used interchangeably. One cool thing about these type of waves over here is that, yeah, you can physically experience it. All right, so if you can somehow shrink yourself down like Ant-Man and crawl in here, if I generate just one frequency through this tube and it's matched up with the characteristic of this tube, as you crawl through over here, you're suddenly going to hear it very loud at the antinode, and you're going to hear silence at the node, very loud at the antinode, silence at the node, so on and so forth as you crawl through. Now, you might think that I'm crazy for telling you to somehow shrink yourself into the tube, but the other workaround is instead of shrinking yourself, how about make the tube nice and big? If you've ever been to the Ontario Science Center, that's why they have that tube out there, that bright, beautiful, I think, yellow colored tube. They want you to crawl through it. So they've already done all the math and calibration so that there will be an antinode on the outside and nodes in the inside. So as you crawl through it, you'll get louder and quieter, just to prove to you that this crazy looking picture over here, or even the ugly looking dotted thing, it is true. It will happen. Okay, something fun to try out when you guys have the chance. Student has a question?
Sorry, I'm just a little bit confused by the picture. Which one is the incident wave and which one is the, because it says that that one's the incident wave and that one's the incident wave.
Okay, so let me animate it for you, because that's one of the problems about textbooks. Textbooks only show a static image. Even my PowerPoint over here, this is a static image as well. I'm going to save it for the next day to show you the animation, because I just want you guys to understand what's going on in the formula in the first place, master the formula, then I'll show you the true to life thing of what's really happening, because it's very trippy and you have to wrap your head around what's really happening. Okay, so this is what you'll copy in your notes, and here's the slightly upgraded animation. If you're talking about the red wave, where mathematically speaking, it just coincidentally becomes a crest on the outside or at the edge, then it's going to reflect back also as a crest. And if hypothetically the wave is just timed in such a way that it makes it to the edge as a trough, as you can see right over here, it's going to return back also as a trough to abide by what's happening right over here. Does that clarify your question?
Yeah, thank you.
Okay. And as I said, that's the problem about having static images. Dots, they're terrible. This kind of helps. Having a PowerPoint helps even more, but it's really something that's a dynamic environment. In other words, every snapshot that you take as a fraction of a second goes by, it's a completely different picture. Okay, so again, I'll tell you what's really happening the next day. Right now, we'll just accept that these pictures, which is what you'll get in your textbook anyways, is valid and true. Okay, now let's apply this towards tubes. Okay, because there are two types of air columns that exist, and these are just the technical names for it. All right, for example, if I have this tube over here and then I seal off one end, this is classified as a closed air column. That does not mean that both sides are closed, because if both sides are closed, the sound will never escape. So when you describe a closed air column, it just simply means that one side is closed and the other side is freely able to breathe. That's a closed air column. Okay. All right. So let's talk about the science of what's happening inside this closed air column. Now, one of the factors of the pictures that we're drawing over here is that it's dependent upon the length of the column, the temperature of the air, which is the speed of sound, and the frequency you're trying to pass through this. Okay. So that's why these tubes over here will only resonate at certain frequencies. And that's what we're trying to get to right now. So the first time where it's going to make a very loud sound or get loud at a certain frequency is if, as you can see in the setup over here, the far end over here behaves as a fixed end reflection because I close it off. And here being open, that behaves as an open-ended reflection. How will we draw that? Well, again, we have a tube that looks like this, and I didn't animate it out perfectly, but you would have a tube, and the tube has to behave like this. It has to behave like a node at the fixed end, and it has to behave like an antinode on the open end. Okay, so the first time that this will occur is with a tube with that length right there. But if you stare at this right now, it's not a full wave, is it? Right? When you end up seeing this, well, that's only just that little part of the entire picture. and this only works out to 1/4 of the entire wave. Okay, so a wave of the same total wavelength or same rate of curvature. Here's the second scenario where you're going to have a resonant pattern occurring. Again, at any wall, it's going to behave like a node or a fixed end reflection. And anytime where there's an opening, it's going to behave like a free end or an open end reflection. So we haven't broke those laws yet. It's going to be closed on or fixed on this side and open on the other side. Sure. O and F if you need to write that down. Okay. Or closed and open, however you want to describe it. Closed and open, sure. I'll use those letters. Okay. So it's going to behave like a closed end reflection on the fixed end, and it's going to behave like an open reflection on the free end. Okay. And yeah, you can regenerate this property again with a curve that looks like this. Yet again, we're abiding by the same rules. You'll see that an antinode, I'll just do this in a different color. Okay, you'll always see an antinode being formed on the open end. So it's going to be an open end reflection. And on the far side, it's always going to behave like a fixed end reflection each and every single time. Okay, and this starts to become an arithmetic pattern. Right, you'll see that the differences between one versus the next increases by the same rate. All right, you'll notice that, for example, the second case, it is increased by an additional gain of lambda over 2. The third example is lambda over 2 plus an additional lambda over 2. Just don't forget that you have this initial part over here, like the original story, which, yeah, I'll color that differently, okay, because the story started off with 1/4. So lambda over 4. Lambda over 4. Lambda over 4. Okay, so in the very first occurrence, you'll see that resonance occurs at 1/4 of a wavelength. Then the pattern happens again at 3/4 of a wavelength. Then it happens again at 5/4, then at 7/4, so on and so forth. All right, so this is an arithmetic sequence. So as I mentioned, you have an open end reflection over here. You have a closed end reflection, OC, OC, LOSCD, OPEN. And again, the first time it occurs happens at 1/4 wavelength. The next one, if you take a look at it, it's not a full wavelength, because a full wavelength would look like that, right? A full sine wave. You're only seeing 3/4 of it. So 3/4 lambda. In the next example, you can see the full wavelength, plus you can see another 1/4 as well. Right, so for the next one, it happens at 5/4 lambda. So it is an arithmetic pattern, right? And with arithmetic patterns, you can create a formula to describe what the outcome is. Now, because we're pressed for time, I'm not going to go through the derivation of it. If you're familiar with arithmetic sequences because you're in grade 11 already, this is effectively one where, again, if you're trying to solve for Tn is equal to A plus n minus 1 d, your A term is equal to lambda over 4 because that's your first term. And you can see that you're incrementing gradually by lambda over 2. So you can sub it in, rearrange the equation, clean it up, and before you know it, you'll end up with this magical formula here. All right, unfortunately, I have to cut to the chase today. So that's the formula after you've gone through your arithmetic sequence equation. For those that are in grade 11, I encourage for you to try it out. There are others that are just in grade 10, so you haven't seen the formula yet. Okay, but it is derived from a pattern that's described in another discipline of education. Okay, so this is the formula that can tell you how long a tube needs to be so that it'll resonate properly at a given wavelength. Okay, so the first question is, what is the first and second resonant wavelength of a closed air column given these parameters over here? Okay, just to speed things up and cut to the chase, I'm going to answer the question right now. At 24 degrees Celsius, remember that you need to use this formula. Vs is equal to 331.4 meters per second plus 0.606 meters per second per degree Celsius times your temperature. Okay, so you're going to sub in 24 degrees Celsius in there. And once you've done that, you're going to get to an answer. Did I have it written down? Yeah, it's going to work out to 345.944 meters per second. All right, so now we have V, but we're trying to solve for lambda. Okay. Another thing that's given to you right now, if you state this as your new sets of givens, is that since you just calculate out your V and you know that F is equal to 512 Hertz, well, you have sufficient information to find out wavelength. Since V is equal to F lambda, then therefore lambda is equal to v divided by f. So 345 meters per second. I'll add a few more sig fig because this is an intermediate calculation, divided by 512 hertz, and it looks like it's going to be around 60-ish. Yeah, 67.57. So 67.57 centimeters. I'll just leave it in meters for now. Okay, so now we know the wavelength of the property of the sound. So the air temperature is at 24 degrees Celsius, and I'm using a 512 hertz tuning fork to do my experiment with. I think I put it away. I'll take it out afterwards. Okay, now with that, I'm going to place it on top of a tube. All right, now if the tube length is too long or too short, if I place it on top, the tuning fork, even though it's resonating, not everyone in the classroom would hear it. But if I make the length of this tube just long enough, it will cause the sound to amplify. All right, and that's what we're trying to figure out right now. What are the lengths that will allow it to amplify? So we're going to solve for the first time where it occurs, or its first resonant length, and then we're going to solve for it the second time, or its second resonant length. Okay, so again, we're going to use the formula up above, but we're going to have n is equal to 1 for the first case. So L1 is equal to 2 times 1, subtract 1 over 4 lambda, or L1 is equal to 2 minus 1. Sorry, 2 times 1 is 2, minus 1 is 1 over 4. So L1 is equal to a quarter lambda. So a quarter of 0.6757 meters, it works out to roughly 15 or 16 centimeters. No, 17 centimeters. So it works out to 16.9 centimeters. And I would demonstrate this in the classroom. We do have a machine that you're able to change the length of the tube. And the moment that the length of the tube works out to 17 centimeters, and I have a tuning fork right above, everybody will hear it nice and loud. Unfortunately, here at home, I don't have that equipment, so you have to take my word for it. That's the first time it's going to get loud at 17 centimeters. Okay. And it'll get loud again at another occurrence as well, which is when the tube is much longer, right? And that's when it behaves like the second picture over here. Okay, so the first one, if you're curious about where the numbers match up, we're talking about this number over here, the length of the tube. So L1, the first occurrence where it's going to get really loud for a 512 hertz tuning fork will be at 17 centimeters, roughly. Okay, the second time around, it'll be much longer than 17 centimeters. We have to sub it into the equation for the next order of resonant occurrence. 2 times 2 is 4, minus 1 is 3. So yes, L2 is at 3/4 lambda, as we mentioned earlier. Okay, so 3/4 of this 0.6757 meters works out to 50.7 centimeters. Can you leave it in meters? You can, but as you can see, when I write it on centimeters, it's easier on the eye. That's the reason why I chose centimeters. So the resonance happens at the whole tube contributes towards the resonance. Where do you hear the sound? You hear the sound through the opening. So yes, you'll hear the sound through the antinode over here, right? But it's the whole nature of the tube itself and its length that causes it to resonate that loud. N is the order, right? So for example, the first one is L1, the second one is L2, the third one is L3. So this is the order of resonance. So the first time where it resonates, the second time where it resonates, the third time it resonates. L is for length. So you can also call it first resonant length, second resonant length, and third resonant length. You could call it that as well. Okay, so that's what the letter N is for. 1, 2, and 3. Why are the units different from lambda? It isn't. Remember that when you divide meters per second, I'll just do this in red, meters per second, and you divide it by hertz, remember that hertz has the same meaning as 1 over second, right? That's what a hertz is, per second. Well, this is a fraction divided by a fraction, so that's also equal to meters per second times seconds over 1, which will give you meters. That's why your final answer is in meters. Where did I get V from in the example? I haven't erased it yet. Remember that this is at 24 degrees Celsius. And at 24 degrees Celsius, this is an exercise from the second night's homework. You're supposed to use the formula and calculate that out. Okay, and yesterday I've already proven to you why the formula looks the way it does. Okay, now if you're wondering why am I doing it in centimeters and meters, as I said, it's really upon what's easier for the eye to see. all right? Because this has the same meaning as 0.169 meters. They are both correct. There's nothing wrong between the two. But what's easier for you to read? Most of us already know that 16.9 centimeters is this long without even pulling out a ruler, right? It's probably the length of your hand. That's why I chose centimeters, all right? So again, as I mentioned many times, the unit that you choose really at the end is the one that you think that the reader will best interpret, right? That's when you choose between millimeters, meters, or kilometers. It's the one that's the easiest on the eye. So there's no strict rule. The only unspoken rule is that it's ideal to have values greater than 1. That's what you want to set it to, right? 16.9 is greater than 1. That's why that looks better than 0.169. Could you have used 169 millimeters? Yeah, that's fine as well. That is perfectly fine. There's nothing wrong with it, all right? But it gets to a point where it gets ridiculous. For example, if you don't want to write down 1, 2, 3, 4, 5, 6 millimeters, that is the hardest thing for anyone to read because nobody knows what that is. It just looks like a big number. But if you write it down as 1, 2, 3.456 meters, then everybody gets it, right? If you've ever been on track and field before and you've done the 100 meter dash, now you know the size of this. It's longer than that by a bit, okay? So that's why you choose a unit that's easier on the eyes for someone to interpret. That's why I chose it in centimeters. Nothing wrong about the other way around, but it's going to be harder for people to pick up. Okay. Again, we have this thing called a resonance, closed air resonance column at school. What they do is that they fill it up with water, all right? Because the water will behave as the boundary, right? So the sound will bounce off the water and reflect and transmit back up because you're going from a medium to something that's super dense. Okay, so the water, you can easily fill it up to make it higher, or you can drain it on the other side to make it lower. And that's how you're able to quickly raise it up and down to get to that sweet spot and prove to the class that this stuff is true. Unfortunately, I can't prove it here, but the next part of this lesson, I can prove to you because I have a piece of equipment for it. Okay, why doesn't it show the half lambda? I'm not sure what you're talking about. Why doesn't it show the half lambda? Okay, now if you're asking about, again, it's because I'm pressed for time right now. All right, I do want to get through this lesson. It's already 10:07. Okay, so I don't want to go through the small intricacies, but yes, what is happening here is that you start off at a quarter, then you add another half to the quarter. Then you're adding another half to that previous half to that previous quarter. That's what you are literally doing, all right, each and every single time. So it is an arithmetic sequence. So if you're familiar with the arithmetic sequence, Tn is equal to a plus n minus 1 d that you would learn in math class. Not everyone has. A term is 1/4 lambda, and d is 1/2 lambda. And if you sub it into here and you work it through, you will definitely get to this formula here. It will work out, okay? I don't have the time to prove it for you right now. It will work out. Maybe later on I can prove it to you, okay? Again, I do need to move forwards. I hope there's not any other questions on this, okay? Because now I'm going to talk about the next type of tube, which is called an open air column. And an open air column is one that simply is defined by one where both sides are open. In other words, you'd expect to have antinodes forming on both sides. Okay, so that's an open air column when both sides are open. Closed air column, one side's closed, it has to breathe. The other side has to be open. Okay, so closed air column looks like this: closed and open air column, open, open. Okay, so again, this is the first time where resonance may occur. All right, you have a tube where it's open on one side, open the other side, fixed in the middle. This is the first order of resonance. You'll notice that this does not equal to a full wavelength. A full wavelength would be from crest to crest. So this is just half a wavelength. That's all you see so far. Now, this is the only time where it can resonate. It can actually resonate at double this length as well. Okay, again, we haven't violated the rules. At the open end, we form an antinode in both these cases here. In the first example, you'll see the length is half a wavelength. The second one, you'll notice it's from crest to crest or from trough to trough, a full wavelength. So the first one is 1/2 lambda. The second occurrence is lambda. The third case over here, again, we haven't broke the rules yet. It's still antinodes on both sides. But now when you look at it, you have a full wavelength plus an additional half a wavelength. So yes, you could derive a general formula for this as well. If you use Tn is equal to a plus n minus 1 d for arithmetic sequences in math class, a term, in this case over here, starts off at half a lambda. And you are incrementing by half a wavelength at each successive pattern. Okay, so when you sit down and you go through all the number crunching, the formula simplifies down to just this. I'll just erase it all. Okay, it does simplify down to just this formula over here. Okay, so now we've learned two formulas so far. ln is equal to 2n minus 1 over 4 lambda, and this one over here, which is ln is equal to n over 2 lambda. Just to let you guys know, on a test, I will give you both of those formulas, no big deal, but you need to know which one is for which scenario. Okay, you need to know that this one over here is for an open air column, and the one with the 4 in there is for a closed air column. Again, these are lengths that which cause the sound to get very loud. So if I have a tube that's this long, it will make that frequency very loud. I can make it this long, and the same frequency will get loud. I can make it this long, and the same frequency will get loud. If I make it any longer or any shorter in between, it won't work out. As I said, everything has its own natural resonant frequency, and it's a characteristic of the object. You modify the object, you've affected its resonant frequency. How many lambda are there in the third open air column? It's in this case over here, it's called 3 over 2 lambda. You have a full wavelength, as you can see over here, plus another half more. Right, so it's a full plus a half. Whoops, plus a half. Full plus a half gives you 1.5, or as an improper fraction, 3 over 2. That's why if you sub in n as 3, you're going to get 3 over 2 for this guy over here. The first one is L1, the second one is L2, and the third one is L3. This picture is just to show you that you can solve these problems in two different ways, okay? You can either have one where you're talking about the same exact frequency, but you're making the tube longer and longer and longer. Or you can say that, hey, I just want a tube to be this long, and that's it. Well, what I'm going to change is the frequency of sound that I inject in here, right? Remember that frequency is correlated to lambda. It's an inverse correlation, but still a correlation. All right. So in other words, multiple different wavelengths or multiple frequencies can resonate with a tube of the same exact length. That's all this picture is trying to show you. Okay. You can either stretch out the tube to fix the frequency, or you can keep the tube the same length but inject different frequencies in it, and it'll still resonate successfully. You can do this with either a closed air column, or you can repeat it again with an open air column. And that's what my next example is all about. Okay, example number 2, I'm going to show you a case where I have a fixed column. I have a column where both sides are left open. All right, so the tube will always be at, 82 centimeters. Okay, so the tube will always be at 82 centimeters. What I will change is the frequency that I inject into this tube, and you'll be able to hear that it can resonate at not just one frequency, but it can resonate at as many as 5 different frequencies for the same exact tube. So the room temperature here right now, because I'm doing a live demo with you guys right now, is roughly around 24 degrees Celsius. Okay, so at 24 degrees Celsius, we have to first do that initial calculation of finding out the speed of sound. So the speed of sound in my basement right over here is 331.4 meters per second plus 0.606. If a student has a question, please type it away. Times the temperature of 24 degrees Celsius. So we just figured out that, yes, Vs is equal to 345.944 meters per second at 24 degrees Celsius. Okay, so I can erase all this stuff now. That's a constant. Another thing that's a constant is the length. I'm not going to change the length. It's always going to be at 82 centimeters or 0.82 meters. What can change, however, is the wavelength of sound that I allow to pass through the tube itself. Okay, so let's go through these occurrences here. Here's L1. All right, you'll see that this is an open air column. So Ln, if Ln is equal to n over 2 lambda, then L1 is equal to 1/2 lambda. That's my first occurrence. Okay, and L1, the length we know already, it's 82 centimeters. So lambda is equal to 2 L1, or lambda is equal to 2 times 82 centimeters, which gives you 1.64 meters. Again, you want to convert to meters at some point. Okay, so the wavelength is at 1.64 meters, and you know the speed of sound is at 345.944 meters per second. With those two givens over there, we can find out the frequency that will resonate beautifully in this tube over here. Okay, so the frequency in the first order of occurrence, well, frequency is equal to, well, we arranged it before, V over lambda. Okay, so 345.944 meters per second divided by the wavelength of 1.64 meters. When you sit down and crunch it out, you're going to get 211 hertz. Okay, so the first occurrence of resonance where the tube is resonating at half the wavelength, it will occur at, it will resonate at 211 hertz. So the first case will be at 211 hertz. Now for L2, and maybe I'll do it in a different color, okay? For L2, one small change. L2 is equal to 2 over 2 lambda, right? So what do we know about this? Lambda is just equal to the length of the tube. So our lambda is equal to 0.82 meters. In other words, we're taking the wave and we're squishing it in. And hopefully you can see that in this picture over here. In the second case, we're just squishing the wavelength in. So now we're having a full wavelength squished in there. By squishing the full wavelength in there, we've affected the frequency that will resonate at. So frequency, again, is equal to speed over wavelength. So 345.944 meters per second divided by lambda, which is 0.82 this time around. That will give you an answer of 400 and something, 423, I believe. 422. Okay. Yeah, I'll color code one more example. We'll do L3. Sorry, I wasn't that efficient in subbing everything in here. But L3, when you sub it in, it's going to work out to 3 over 2 lambda. In other words, lambda is equal to 2/3 of L3. And 2/3 of L3, I'll just write it out, 2/3 of 0.82 meters, because again, the length is always fixed. Will give us 0.54 meters. Frequency is equal to V over lambda, just like before. And unfortunately, because I'm out of space, I'm just going to simply calculate it out. As you know, it's 345.944 divided by the wavelength of 0.54, and that will give you 640 hertz. Okay, so 640 hertz for this one. Okay, for this tube to resonate at its lowest frequency, it's usually very hard for me just to spin it around. So I'm just going to blow from the top, and we'll see the corresponding number here. Did you guys see that? 211.8. Okay, 214, but you get the idea. You're getting around 211. All right, and the more exciting part is when I try the higher orders of resonance. Right, you may know that to make this thing resonate, all you got to do is just take it and start whipping it around. So the first order of resonance, it's tough to do. You have to blow through it to make it happen. But the rest of it, all you have to do is just simply spin it around. Isn't that amazing, the numbers? 421, 422. What about the next one? Look at that. All right, we're only off by 1 or 2 hertz. How about the next one? It's not too bad either, right? 850 versus 844. Again, that's less than a 1% error. How about the last one? And that's the hardest one because I keep on whacking into things. And there you have it. Okay, physics does actually work. The outcomes are real, and it is measurable, and it is all provable. I think that's the coolest thing about physics, right? Things do work out. So this is a story that just tells you that, you know, you have a resonant column of some mystery length and a second one of another mystery length. Okay, you don't know what the lengths are, but you know that they differ by something. What is it? Oh yeah, one length is at, you know, almost a meter, and the other one is at 1.5 meters. Okay, almost 1 meter, 1.5 meters. And you're trying to figure out, you know, what is the frequency that both of these resonate at? Okay, because as I said, with the tube lengths, you can affect one thing or another. You can either affect its frequency at its first order of resonance, or you can have multiple frequencies resonate with the same tube length. And we want to see what's in common between these two. All right. One thing about this question over here, it tells you that these two differ by an order. In other words, if this is one length where it resonates at, this is the next one on the list. And one thing that you'll notice is that when you differ between two different orders in a closed air column, they differ by half a wavelength. Right? Every time that you make it slightly longer, you're always adding lambda over 2. So what that tells you is that the differences between these two numbers over here, 1.56 and 0.94, tells you lambda over 2. And that's what we're going to do. We're going to subtract these two values, and it represents half a wavelength. Okay, so if 0.62 meters represents half a wavelength, then the real wavelength of the sound, in other words, the thing that I'm highlighting right over here, that true length over here works out to 1.2 meters. And once you know the wavelength that's being generated, that's in common between these two here, you can find out the corresponding frequency by dividing speed of sound by the wavelength. So you simply do that, and that's the resonant frequency. So 279 hertz will resonate at a tube that's this long, and it'll also resonate at a tube that is this long. Okay, and I'll leave that for you for today's lesson.